Welcome to Talk Tensors. Today we're shifting gears a bit. We are not looking at a news article or a tech blog. We're doing a special deep dive into a single academic paper. A paper that, and this is no exaggeration, really divided the history of machine learning into before and after. We are looking at Attention is All You Need, published at NEPS 2017 by a team from Google Brain and Google Research.
Yeah, it is. I mean, it's arguably the most influential computer science paper of the last decade.
Yeah.
It really marks the birth of the transformer architecture, which, is the engine under the hood of basically every major AI breakthrough we see today.
And we have to talk about that title right off the bat. Attention is all you need. It just sounds so incredibly bold, doesn't it? It feels like they were throwing down a gauntlet, like forget everything you know, just look at this.
It was definitely a statement. At the time, the field was dominated by very specific architectures. The title is actually a literal description of their proposal, but it also carries this subtext of, clearing the board. They were saying you don't need the complex recurrence or the convolutions everyone else is using. You can rely solely on attention mechanisms.
So essentially, they looked at the industry standard and just said, nope, we don't need any of that.
Pretty much. And our mission today is to unpack exactly why they said that. We need to understand how this shift allows for massive parallelization, drastically faster training times, and why it produces such better results.
Okay, let's get into it. To really appreciate the solution, we have to understand the problem. What did the world look like in, say, 2016, right before this paper dropped?
So the landscape was completely dominated by recurrent neural networks, or RNNs. Specifically, you had models like long short-term memory LSTMs and gated recurrent approaches. If you were doing language translation back then, like Google Translate, this is the gold standard.
And how did those models actually work? What was the core idea?
The keyword is recurrent. These models process data sequentially. So imagine reading a sentence. You read the first word, you process it, you generate what's called a hidden state, basically a memory of that word, and you pass it to the next step.
So it's like a relay race. The second runner literally can't start until the first runner hands off the baton.
That is a great analogy because it highlights the biggest flaw.
Right.
The bottleneck. You cannot parallelize that process. You absolutely have to wait for time step t-1 to finish before you can calculate time step t.
And in modern computing, waiting is a dirty word. We have these massive GPUs that want to do a million things at once, and the RNN is forcing them to stand in line.
Exactly. This sequential nature just precludes parallelization within training examples. If you have a sentence that's 50 words long, you have to do 50 sequential steps. And this becomes a huge problem with long sequences because memory constraints limit how you can batch data. The longer the sequence, the slower and more expensive it gets.
The paper mentions some attempts to fix this, right? Things like factorization tricks and conditional computation.
There were attempts, yes, but those were really just optimizations. They were like Band-Aids and a broken leg. They improved efficiency a little bit, but the fundamental constraint was still there. The model was still sequential at its core.
And there were also competitors trying to use convolutional neural networks, right? I think the paper mentions ByteNet and ConvS2S.
Right. And those models tried to use convolutions, which are great at processing blocks of data at once. They did solve the parallelization problem, but they introduced a totally new issue. In those models, the number of operations required to relate two words grew with the distance between them.
So if I have a sentence where the subject is at the very beginning and the verb is way at the end, the model struggles to connect them.
It struggles, yes, significantly. In some cases, the difficulty grew linearly, in others logarithmically. But the point is, the further apart two pieces of information were, the harder the model had to work to see that connection. And that makes learning long-range dependencies, which is, crucial for understanding language, very difficult.
And here is where the transformer just changes the entire game.
It really does. In the transformer, the number of operations to relate signals from two arbitrary positions is constant. It's O1.
O1. So it doesn't matter if the words are right next to each other or 500 words apart.
The computational cost to connect them is identical. It effectively shrinks the distance between any two words in a document down to zero.
That is a massive paradigm shift. It's moving from reading sequentially to just looking the whole page at once. So let's get into the how. What does this transformer actually look like under the hood?
Okay, so at a high level, it still follows an encoder-decoder structure. That's pretty standard for translation. You have an encoder that reads the input, like an English sentence, and a decoder that produces the output, like the German translation.
But the inside is completely different.
Completely. Instead of recurrence, it uses stacks. The encoder is a stack of 6 identical layers. The decoder is also a stack of 6 identical layers.
6 layers deep, and inside these layers we find the magic ingredient, self-attention. We hear this term constantly now. But what is it, really? The paper uses these terms: queries, keys, and values.
This is where people can get a little tripped up, so let's slow down. The paper defines attention as mapping a query and a set of key-value pairs to an output.
I have to be honest, queries, keys, and values sounds like I'm managing a database from the 90s. Why those specific terms?
Oh, yeah, it's a metaphor borrowed from information retrieval, but it works. Think about like a library filing system. Suppose you want to find a book. You have a topic in mind? That's your query.
Okay, I'm the query. I'm looking for info.
You walk to the filing cabinet, the tab on each file folder, the little label that tells you what's inside. That is the key. You compare your query, what you want, against the keys, the labels.
And when I find a match?
When you find a match, when the query and key align, you pull out the contents of that folder, the content inside. That's the value.
So in the model, every single word is looking at every other word, acting as a query and checking if the other word's keys match what it's looking for.
That's the intuition. The final output for that word is a weighted sum of all the values. And the weight for each value is just determined by how well its key matched your query. If it's a strong match, you pay a lot of attention to that value.
The paper calls this scaled dot product attention. I see the formula, but let's walk through the mechanics.
Sure. It's basically a 3-step process. First, the model takes the dot product of the query and the key. In vector math, a dot product is really just a similarity score. It tells you how much 2 vectors point in the same direction.
Okay, so a high dot product means high similarity. I'm very similar to this word, not so much to that one.
Exactly. But there's a catch. As the dimension of these vectors gets larger, those dot product scores can get huge. And if you feed huge numbers into the next step, the softmax function, the gradients get incredibly small.
Which means the model stops learning because the signal is too weak.
Precisely. It kills the training process. So step 2 is the scaled part. They divide that raw score by the square root of the dimension of the keys. This just shrinks the numbers back down to a manageable range so the gradients can flow.
Smart. And step 3?
Step 3 is applying softmax to turn those scores into probabilities. Percentages that all add up to 100. And then you multiply that by the values. So you end up with a final vector that's a blend of all the relevant information from the other words.
Now, the paper doesn't just do this once. They use multi-head attention. Why do we need multiple heads? Isn't one attention mechanism enough?
Think about a complex sentence, like the chicken crossed the road because it was hungry. If we look at the word it, what should it attend to?
Well, it refers to the chicken.
Right. So one attention head might focus on that noun-pronoun relationship, but it is also the subject of the phrase was hungry. So another head might need to focus on the grammatical structure. A single head tends to just average things out. It can only focus on one dominant relationship at a time.
So by having multiple heads, the paper uses 8 of them. It's like looking at the sentence through 8 different lenses at the same time.
That's it exactly. One head looks for who, one looks for why, one for grammar, one for context. It lets the model jointly attend to information from different representation subspaces.
Okay, so that's the attention mechanism. It gathers all the context. But looking at the diagram in the paper, there's another big block in each layer, the position-wise feed-forward networks.
Yeah, this is a crucial piece that often gets overlooked. Attention is just a mechanism for gathering information. It says, hey, these other words are relevant to me. But it doesn't actually process that information very deeply.
It's just the retrieval step.
Correct. So once the attention layer constructs this weighted vector of context, it passes it to the feed-forward network. This network is applied to each position separately and identically. It's just 2 linear transformations with a ReLU activation in between.
So if attention is the looking, the feed-forward network is the thinking.
You could say that. It takes the context gathered by attention and transforms it into a richer representation that the next layer can use. And, very importantly, because it applies to each position independently, this part is also fully parallelizable.
I want to touch on the 3 different ways they use attention, because it's not just one big blob.
Right, they use in 3 specific contexts. First is encoder-decoder attention. This happens in the decoder. The queries come from the decoder, but the keys and values comes from the encoder, from the original sentence. This lets the decoder look at the entire input sentence at every single step.
That makes sense. Then there's encoder self-attention.
That's where every word in the input attends to every other word in the input. This builds a rich understanding of the sentence before we even start translating.
And finally, decoder self-attention.
This one is tricky. In the decoder, we are generating the output word by word. So when we're generating, say, the third word, we can look at the first and second words. But we absolutely cannot look at the fourth word because we haven't generated it yet.
That would be cheating.
It would break the whole model. So they implement masking. They basically takes the attention scores for all future positions and set them to negative infinity. When the softmax function sees negative infinity, it turns the probability to 0. It's like putting blinders on the model so it can't peek into the future.
Okay, so we have this incredible parallel architecture, but there is one huge problem we haven't solved. If I feed it the dog bit the man and the man bit the dog, without RNNs processing them in order, doesn't the model just see a bag of words, dog, man, bit, that?
That is the fundamental weakness of pure attention. It has no inherent concept of order or sequence. It is what's called permutation invariant.
So how did they fix it? This leads us to positional encoding. And this is one of the weirdest parts of the paper. They didn't just number the words 1, 2, 3.
No, that would be too simple and would have problems generalizing. Instead, they injected information about the position by adding sine and cosine functions of different frequencies to the input embeddings.
Wait, hold on. Sine waves, like trigonometry. How does a wave tell the model where a word is?
Think about a clock. The second hand moves fast, that's a high frequency. The minute hand moves slower. The hour hand moves very, very slow. If I tell you the positions of all three hands, you know exactly what time it is, right?
Sure.
The authors did something similar. They use a whole spectrum of frequencies. Some dimensions of the vector wiggle really fast, some wiggle slow. By combining all these, every single position gets a unique signature based on the interference pattern of all these waves.
Why go through all that trouble instead of just, learning a position vector?
Two big reasons. First, it allows the model to easily learn to attend by relative position. The math works out so that the position pos plus k can be represented as a linear function of position pos. So it's easy for the model to learn, focus on the word 3 steps back. Second, it lets the model extrapolate. If you train on sentences of length 20 and suddenly you get a sentence of length 30, the sine wave pattern just continues naturally.
It effectively gives the model a continuous ruler that can just stretch infinitely.
That's a beautiful way to put it.
So they built this incredible theoretical machine. The big question is, did it work?
Oh, it worked spectacularly. Let's look at the training first. They trained on the WMT 2014 English-German dataset, about 4.5 million sentence pairs. They used 8 NVIDIA P100 GPUs.
Which is a decent rig, but not a supercomputer by today's standards.
Right. And the base model trained in just 12 hours. The big model took 3.5 days.
And for context, how did that compare to the competition?
The best models at the time took weeks to train. Weeks. We are talking about reducing training costs by an order of magnitude. This democratized the ability to train state-of-the-art models.
And the quality. Was it a trade-off? Did they sacrifice accuracy for speed?
Not at all. On English to German, the big transformer got a BLEU score of 28.4. That beat the previous best, and that previous best included massive ensembles of multiple models by over 2 full BLEU points.
And for listeners who aren't in the NLP weeds, 2 BLEU points.
It's a leap. It's a huge leap. Usually researchers fight for 0.1 or 0.2 improvements. A jump of 2.0 is a generational shift. On English to French, they hit 41.8, a new single model state-of-the-art.
They also tested it on English constituency parsing to show it wasn't just a translation trick.
Right, on Wall Street Journal dataset. And this is a task about understanding grammar, noun phrases, verb phrases, all that. And even though it wasn't tuned for this, it performed incredibly well. It proved the transformer wasn't just memorizing dictionary swaps, it was learning the fundamental structure of language.
Speaking of structure, I want to jump to the visualizations in the paper. We often talk about AI as this black box, but the attention mechanism actually gives us a flashlight to peek inside.
It does, and this is one of my favorite parts of the paper. Because we can visualize the attention weights, those probability scores, we can see exactly what the model is looking at when it processes a word.
Give us an example of what they found.
So there's a classic problem in linguistics dealing with ambiguous pronouns. For instance, the animal didn't cross the street because it was too tired.
We know it refers to the animal.
Right, but if you change one word,
yeah,
the animal didn't cross the street because it was too wide. Now it refers to the street.
That's just common sense. An animal can be tired, a street can be wide.
Exactly. When they visualized the attention heads, they saw that in the first sentence, the attention for the word it spiked on the word animal. In the second sentence, the attention completely shifted and spiked on street.
That is mind-blowing. The model didn't just look at what was closest. It understood the semantic context of tired versus wide and updated its reference.
And it did this across different heads. One head might handle this kind of coreference, while another is just making sure the verb agrees with the subject. You can actually see the intelligence distributed across these mechanisms.
It really validates the whole attention is all you need claim. It's not just catchy, it's architecturally accurate.
It truly is.
All right, that brings us to the end of the hard science. Now it is time for our favorite segment.
Let's do it.
Welcome to Novel Notions. This is where we take the core mechanics of the paper we just discussed and pitch some outlandish, maybe impossible, but scientifically plausible research ideas.
And the disclaimer. This is for entertainment purposes only. Please do not cite our novel notions in your dissertation. We are not responsible if your advisor laughs you out of the room.
Okay, I've got two for you today. Concept number 1, the infinite context biotransformer.
Infinite context. But the paper talks about memory constraints. That was the whole reason for the O1 path length.
True. But look at section 4. They mentioned that for very long sequences, self-attention could be restricted to a neighborhood of size R.
Restricted self-attention. So instead of looking at every word, you only look at the, say, 100 words around you. That changes the complexity.
Exactly. So here's the pitch. We use this restricted attention to ingest entire human genomes. Millions of base pairs in a single pass.
Current RNNs fail because the sequences are just way too long. They forget the beginning by the time they reach the end.
So you want to treat DNA like a massive language translation problem.
Yes. We use a transformer that is incredibly deep, maybe hundreds of layers, but has a restricted view at each layer. We train it to predict genetic diseases. The hypothesis is that a mutation at base pair 1000 might interact with one at base pair 1 million. An RNN would never see that connection. A transformer, even a restricted one, can propagate that signal up through the layers. So you're relying on the depth of the network to create a global receptive field, even if the individual attention heads are local. It's sort of like how CNN works, but for sequences.
Yeah.
That actually might work. It's basically AlphaFold, but for the whole genome.
Exactly. Attention is all you need to crack the code of life.
Okay, I'll give you a B+ on plausibility. What's concept number 2?
Concept number 2, the universal frequency translator.
This sounds distinctly more sci-fi.
Stick with me. We talked about positional encodings, using sine waves to represent position.
Right, mapping position to a frequency.
So what if we take that literally? What if we replace position in a sentence with time series data from completely unrelated fields? I want to translate sheet music into stock market trends.
You want to translate Beethoven into the S&P 500.
Hear me out. Both are time series data. Both have structure, rhythm, tension, and release. If we treat the position strictly as a frequency domain, we could train a transformer where the input is a symphony and the output is a market volatility graph.
So you're hypothesizing that the structural crescendo in a piece of music maps to a market rally in finance.
Yes. The transformer doesn't know it's music or money. It just sees the relationships between the frequencies. You could translate the sentiment of a song directly into a stock chart.
This is wild. You are conflating syntax, the position, with semantics, the meaning. Just because two things happen in a sequence doesn't mean they share the same grammar.
But that's the beauty of it. It's the ultimate test of the architecture. Can it find patterns where we think none exist?
It's probably financial astrology, but it would be a fascinating experiment in how flexible those positional encodings really are. If you can map it to a sine wave, the transformer will try to attend to it.
That's the spirit.
So, to bring us back down to earth, what's the real takeaway here?
I think we moved from a world of remembering, where RNNs were frantically trying to hold on to the past, to a world of looking.
That's a perfect summary. The transformer doesn't burden itself with memory. It just looks. It looks at everything all at once and decides what matters in that moment.
And that single shift is why we have GPT, why we have Claude, and why AI is moving at the speed of light today.
It all started right here with this paper.
Thanks for listening to Talk Tensors. Keep learning and pay attention.
Because apparently that's all you need.